All right, so worksheet 10 is, well, a little bit of review, but mostly just messing with your head about actually, there's one more thing I do need to tell you in worksheet 10 and concavity. Ooh. Okay, so before we talk about concavity, we want to talk about the language of derivatives. And I just totally made up that. I don't even know what to call it. Because what I'm really talking about is the following. When you have a function and you have some units on the function and units on the input. So input and output both have units, and it looks something like this. You're going to have units of f and units of x. What does it mean when you're talking about a derivative or a slope? Well, it's a rate of change. You know, f could be population, x could be years, f could be temperature, and x could be minutes. It doesn't matter. It just means that two things are changing relative to each other. They don't even have to be connected in any way. There's just a graph that tells you one is this one is this. Okay, so x can be crogs and f can be blots, and I'm just making this up. So if f of x is in blots, units of blots, then f prime of x is in units of blots per crog. Okay, that's all it is. You don't have to understand what it means. You just have to put the language together. And if you want to know what the second derivative is, well, that's going to be in the units of in blots per crog, right? Because blots per crog, sorry, I meant the second derivative. Blots per crog is the units we had up above, and then you just say per crog because you're taking another derivative with respect to f. Which brings me to another important point that's just a cool little thing. Because you have blots per crog for f prime, if you flip this around, you really get crogs per blot. So like at this particular point, whatever this is, if this happens to be 2 blots per crog, then if you look at the inverse function, you have to flip the point around. So like maybe this is point like A, and this is point B, and this is at point AB. At point AB, you'd say, aha, f prime at A is equal to 2. Well, then f inverse has the derivative at B of, well, the reciprocal. If it's 2 blots per crog, then it is a half a crog per blot. Okay, so you just take the reciprocal, woohoo. And this trick only works for the first derivative. You cannot do this with the second derivative. And the reason is, in the second derivative, it's blots per crog. It's not crogs per blot. So the point is, since it's the first one is pure and simple, and you're just taking a ratio of 2 variables, and you're not turning that thing into a new function. So a special deal for only the first derivative is you can take the reciprocal to get some information about the derivative of the inverse function. Okay, cool. And we're going to use that trick later to prove something. So let me make up some other one. Let me just make up something. Okay, I'm just not thinking today. I'm just thinking, okay, what does the worksheet say? So over here we have rain falling in centimeters per hour. Okay, so you have a function of some sort. So this is f. So what does that mean? Well, x is centimeters. Sorry, what am I thinking? Time goes over here. So if x, let's let t be time, it's just easier. And then centimeters would be f of t. So what's the derivative? Is change in y over change in x, or centimeters per hour is the units. The units for f is centimeters. The units for the second derivative is centimeters per hour. And when you do centimeters per hour, what that works out to be is centimeter per hours squared. And maybe you're like, what's a square hour? It's like, no. You're not squaring the hour. You're looking at the second level of change. You're just looking at the secondary effects, because you have already the rate of change, but you're trying to see how fast that rate of change is going. So it's analogous to saying position, velocity, and acceleration. That's what it's doing. Acceleration is how fast something's velocity is changing. So that's why, you know, gravity is 9.81 meters per second squared. I actually had a dream when I was in high school. When I was taking high school physics, I dreamt I was in an elevator falling. It's one of those crazy falling dreams, and I actually woke up because I couldn't get the dimensional analysis to work out. In the dream, I said, how fast am I falling? And I'm like, it's 9.81 meters per second. And I'm like, no, the units are wrong. It's meters per second per second. That's not a speed. That's not a speed. What is that? And I woke up and I'm like, I woke up because in my dream I couldn't work out the dimensional analysis and couldn't figure out how fast I was falling. And I was making a common, literally making a common math or physics mistake, is to use the acceleration when I was looking for the speed. Like, I couldn't tell how fast I was falling in the dream, but I could have said to myself, you're accelerating at 9.81 meters per second. And then I would have been able to continue my dream and you would have never heard this stupid story. But dimensional analysis can really get under your skin. And so anyway, just notice the difference between position, velocity, and acceleration. So meters per second, otherwise known as meters per second squared. Okay, and you write it the same way you would as if m is a variable and s is a variable. You stack them just the same way and you write them just the same way. And I think you're going to have fun doing some of that in web work, actually. There's not a lot of it, but there's a couple web work assignments. I don't think they're in this chapter, but you will have to do it. So what happens now? What if you have, here's f again, and you have, let's say, x and f, and let's make up some more crazy stupid units. Let's say dollars per year. I don't even know what this function's about. Okay, I guess year should be over here then. Something happens as time changes, the dollars are going to change. It's just easier to visualize. You can make a function the other way around. It just is probably not very realistic. Okay, so if we want to ask the following question, first of all, I want to do something that's invertible. So I'm going to change this function to something that's invertible. Okay, never mind, dollars shouldn't be negative, so I'm going to change that again. Okay, so it can be crazy, but it should be invertible. Okay, so what does f inverse of 4 mean? What are the units on that? Well, if the unit on f is dollars, then the unit on f inverse must be in units of years. Okay, so it's telling you at what year is the dollars for. Okay, it's inverting it. So like, since you're inverting it, you're going the other way. So normally when you look at f of x, you take x and you look for f. F inverse takes what used to be the output and looks for the input. So the units also flip around. Okay? And what does it mean if you say f inverse prime? Well, that looks crazy. But what it is you have to actually, like, depending on the problem, you either have to solve. So like if I said f is equal to 3x cubed, I can just solve. So remember, I already told you how to do that in a previous video. I flip the x and the y, take the cube root. I did this on purpose because it's invertible. It's actually, I don't need to worry about that. The sign comes along for free, and so that's good. That's the cube root. I'm just going to write it as 1/3, or I can write it like this. Okay, so you can now go ahead and take the derivative. You can't take the derivative of that because I haven't shown you how, but if you could, you would. And you take the derivative of that and go ahead. But if I asked you f prime at, say, a specific point, A, comma B, you could take advantage of the fact that you already have the derivative of f, and then if you know how this all matches up, you could just take the reciprocal of that and save yourself a bundle of work. Okay, so there's a lot of little math problems where you can get out of jail free by just knowing these little tricks. Okay, now concavity. And I love this because concavity is pretty cool. Concavity is telling you whether, let me just draw a quick little picture. Y equals x squared is the picture I want you to have in your head for positive concavity, or otherwise known as concave up. And just put a minus sign on that to show you what negative or concave down looks like. And what I want you to think about is, I like to think of this, if this is a cup, I'm emptying the cup. Concave down spills water, and concave up holds water. And notice that within concave up and concave down, they both have increasing and decreasing in both cases. Okay? I have this little diagram I like to share that I found to be very effective for calculus students, trying to fit all this together. And let me pause to draw it for a second. Okay, so here's what I like to draw. I draw a circle and then I break it up into 4 pieces. And so in quadrant 1 is an example where I'm decreasing, so f prime is negative, and quadrant 2 is increasing, so f prime is positive. Quadrant 3, f prime is negative because I'm decreasing. Quadrant 4, f prime is positive. So that's just talking about the first derivative. Now we're going to go by and say what's happening with the second derivative. Well, this from here to here is spilling water, and from here to here it's holding water. Okay, so because when it's holding water, the second derivative is positive because it holds water. Positive because it's increasing, right? So negative because it's decreasing, but f double prime is positive because it holds water. And over here, quadrant 1, f double prime is negative because it spills water. And quadrant 2, f double prime is also negative because it spills. Okay? So that's my little memory trick so that you can have in your mind ready an idea of how all these pieces fit together. And I will come back to that again, but that's just my first pass at giving you some little pieces that you can put together. So I think in one of your exercises it may ask you something like, can you come up in your mind with some kind of function that starts off with the first and second derivatives both positive, and then it transitions, so the first derivative is positive but the second derivative is negative. And I'm like, okay, I'm just going to erase all the parts that don't apply to this question so you can see what I'm saying. So if I'm just looking at this part of the diagram and the question says, create a function with f prime greater than 0 where f double prime goes from positive to negative. And I'm like, okay, so you want a positive first and second derivative, so essentially you want this quadrant 4 piece. So I'm going to just kind of put this off to the side for a second, like I'm going to use this in a diagram. And then you want to attach that to one that goes first derivative is positive, second derivative is negative. Just easy like that. You just sort of glue them together and you're like, oh, that's basically what it looks like. And so if you think about these little pieces of circle, they actually work pretty well. I've found that they work pretty well for the student exercises that we tend to dish out to you guys. So hopefully that little trick will just make your life a little easier. Okay? Let me think about this. There's a question in the worksheet about parachute and terminal velocity and air resistance, and I just found it a little bit hard to visualize. So in the quiz itself, I give you a link to a video I like. You don't have to watch the video, just watch a couple seconds because they draw the graph and explain the pieces of the graph. They go further than we need to go because in our story we're only hitting terminal velocity and then the problem ends. But in the problem they go on to tell you what happens when the parachute deploys and they draw out the whole thing. So you only need the first couple segments of that graph. But anyway, I liked that video, so I decided to share it with you. But try the problem yourself first. And then if you get stuck, don't worry about it. Go on to the quiz anyhow because I give you additional assistance on that within the quiz. All right, one more hint on the quiz. There's something, I'm not going to tell you the full extent of this exercise, but it looks something like this. And I just don't like those units. So in the exercise, I converted the units of time to a more recognizable unit of time. And so you'll see. So just warning when you see this one, watch out. I know that's a little tricky, but the rest of the exercises are really easy, and since it's like a matching question, I don't feel that bad for you. But I do want you to think about what this means and work that out. Okay? I think that's it. I think that's all I need to tell you to get you through the worksheet, and I guess I'll see you in class.